when we refer to the strength of an acid or base, we're really talking about its tendency to form ions, its tendency to shift forward and form ions. And so we can think about all these acids and bases as kind of equilibrium systems, where here's kind of the general equation for an acid. An acid is a hydrogen donor. So when I look at this equation, I see that I'm starting with HA, which is really just supposed to represent some random acid, where maybe A minus is something like chlorine. It could be something like nitrate. It could be something like, it could be anything like acetate, H3O2 minus. A minus is just some negative ion from the acid. And the acid, the negative ion, would be attached to a hydrogen. And so if I kind of look at what's happening here, my acid should be the hydrogen donor. It's going to give a hydrogen ion to the water. So we'd say HA is acting like an acid and water is acting like a base. It's accepting the hydrogen. It's removing the hydrogen ion from the solution. Now, if this thing were to go in reverse, then we say, okay, what do those ions have to do to shift backwards? Well, now H3O, sorry, buddy, but you'd have to give your hydrogen back to A minus. So the hydrogen donor on the product side would be called the conjugate acid, and the conjugate base is always the negative ion on the product side, because a base is something that can react with hydrogen. It can accept hydrogen, remove hydrogen from the solution. So here's just kind of a typical equation for any acid, where A minus just represents the conjugate base, or the negative ion that's attached to the hydrogen. Now, when we write equilibrium expressions, then we write them as product over reactant. We raise them to the coefficients in the balanced equation. And remember that we don't use liquids. So we can write equilibrium expressions for these general like acid equations, where it's going to be the product of the two ions all over the initial acid concentration, and we're not going to use the water. Often you'll see the water written in the equation because it kind of shows where the hydrogen is going. It's attracted to these water molecules, where the oxygen ion is really negative. We're just not going to use the concentration of water in any of our calculations. So here's the general expression for the equilibrium constant from an acidic solution. And we call it Ka, where A just stands for the acid dissociation constant. Ka. Now, sometimes you might see the hydrogen on the product side just written as H plus if somebody totally left the water out of their equation. More often, you'll probably see it written as H3O plus. But either are going to eventually lead us in the same direction. More equilibrium constants. We're just going to get a little more specific and call it Ka, in that it's always going to be referring to an acid dissociating, kind of like this equation given to us. And again, A minus just represents some general conjugate base. Now, what happens with a strong acid? Well, strong just means that it dissociates fully. So the more likely it is to dissociate, then the more likely it is that this thing favors the forward. And so we say here that the equilibrium lies to the right, or maybe more often we'd say forward. It favors the forward. Strong means high tendency to dissociate. I mean, sometimes we even say like 100% dissociation. Like a good example of a strong acid is something like hydrochloric acid. Now you might see it written like HCl plus water, forming the I'll put the double-sided arrow in for this one. You might see it forming like the chlorine ion and H3O plus, where the hydrogen is going to be donated to the water. Or sometimes you even just see this like HCl. Sometimes you might not see the water in there, and it might just be like H plus and Cl minus. You might even see HCl with a one-sided arrow, because essentially this thing really does go forward 100%. So that if I had a 1 molar solution of HCl, it is 1 mole of hydrogen per liter and 1 mole of chlorine per liter. 100% dissociation, to the point then where there wouldn't be any HCl molecules that are as molecules. They all split. And so we're going to get a ginormous K value. In fact, like for HCl, Ka is approximately 10 to the 8th power. It's a really big value, meaning that it's almost all ion. Where essentially we do say that these pretty much just go to completion. Almost all the original acid is dissociated. Interesting. Now, if the equilibrium favors the forward, then the conjugate base, which is the chlorine ion, is not a very good base, right? I mean, the job of a base is to pick up hydrogen. That if chlorine is going to act like a base, then it's supposed to take hydrogen away from the H3O and then shift this thing in reverse. But chlorine sucks at being a base. If the equilibrium lies so far forward, the chlorine just really doesn't remove hydrogen. It doesn't shift this thing backwards. And so essentially the chlorine stays chlorine ions and the H3O stays H3O, or just hydrogen ions. That this really doesn't reverse itself. Common strong acids are things that you're probably kind of familiar with, like hydrochloric, bromic, iodic. So most of the halogens, just not hydrofluoric, nitric acid, sulfuric acid, things that we've commonly probably used. Weak acids then have their equilibrium lying to the left, or maybe more often we would say the reverse. And then they have a really small K value, that if the equilibrium expression is product over reactant, and if this thing is not going forward, so maybe like if I look at this initial example with the generic acid, if this were a weak acid, then weak meaning that it really does not dissociate much. Sometimes it might only be like a 1% dissociation. Maybe only 1% of the original molecules dissociate to form hydrogen ions. So you're not going to get much hydrogen in the solution if that original acid only dissociates by like 1%, 5%, even 10%. Would still be a pretty weak acid. So yeah, that's where I'm going to get a small K value then. That if this thing does not go forward and it does not dissociate by much, then it's favoring the original acid. It's favoring the reactants. So there's not going to be a lot of product ions. It's mostly the HA. Oh yeah, so then that's going to give me a small K value. All of these K values here for the weak acids are like 10 to the negative something power. Okay, that kind of makes sense, right? So check out this example. I really love this. They're telling me that hydrofluoric is a weak acid. Now they might also give me an equilibrium constant. They might be like a Ka value listed. And if the Ka is small, like 10 to the negative something, that's another hint that the acid they're referring to is weak. So you don't have to memorize all these acids. Are they strong? Are they weak? It's good to know some of the common strong acids like hydrochloric and nitric and sulfuric. But there's way more acids that are weak. Most acids are weak. And often they'll either tell you or they'll give you a Ka value. And if I see then that the Ka is 10 to the negative something, then I know it's weak, that it doesn't form many ions. So they're telling me here that this is a weak acid, which means then that the equilibrium favors the reverse. Now here you could see it written as is, or maybe more often we would see it written with water as part of the equation because it kind of shows where the hydrogen goes. So if HF hydrofluoric is acting like an acid, it's going to be a hydrogen donor. So it's going to give a hydrogen to the water. So you'd be left with that fluorine ion and H3O plus. So the transfer of hydrogens from the acid to the base. And in this case, water would be acting like a base. It would be acting like the hydrogen acceptor. Okay, so what if I had a 1 molar solution? And I don't care about the amount of water, but if I had a 1 molar solution and this is a weak acid, it is not going forward by much. I mean, maybe again, like maybe 1%, maybe 5%. And so the amount of a fluorine ion and H3O is going to be way less than 1 molar. It'll be much less than 1 molar. Okay, so the hydrogen ion will be less than 1. Yes. The fluorine ion will also be less than 1, which, by the way, H plus equals H3O plus. Those symbols can be used interchangeably, whether we just say H plus or whether we show that the hydrogen is attached to a water molecule. Same gig. To know the fluorine is not going to be greater than 1, it's going to be much, much less than 1 because this is not going forward at all. Now I can say that the hydrogen ion or hydronium and the fluorine will be the same. Now eventually we'll kind of look at that, like how do I figure out how much hydrogen or how much fluorine is in the solution? And all it is a cute little ice table with your Ka value. But for now, all I can say is that they're going to be way less than 1, and I know that they'll be the same. The fluorine and the hydronium or hydrogen will be the same because they're produced at a 1-to-1 ratio. Now the difference with a strong acid would be like if I had a strong acid, let's say it's HCl. It's water. And the hydrogen is donated again so that I have chlorine ions and either H plus or H3O plus. Now let's say I had a 1 molar solution and I know that this is a strong acid, so it dissociates 100%. Well, now I know that this is going to be exactly 1 molar chlorine and 1 molar hydronium. And eventually this would be gone. There would be no HCl molecules. Everybody splits. Not the case with a weak acid. The concentration of those ions will be much less than the concentration of the original acid.